let us now give many examples to get a grasp of this concept. Examples. So, the first example is we have already seen a couple of examples. In fact, most of these properties are obtained by noting what are the properties in say R2 or R3 which are special and which we would like to generalize, right. So, let me now just give you the more general Rn. Rn is just the Cartesian product of R with itself n times. So, it is x1 up to x2, x1, x2 up to xn, where each of the xi's are real numbers. So, this is an ordered tuple. Again, 2, 3, 4 is not the same as 4, 3, 2. The order matters. And what is the addition and the scalar multiplication? As is to be expected, suppose x1, x2 up to xn is an element in Rn, and y1, y2 up to say yn is an element in Rn, then we define. So, when I put a colon followed by an equal, it means that we are defining something. Here in this case, we are defining the vector addition. What is this? This is x1 plus y1, x2 plus y2, so on up to xn plus yn, component wise, right. So, for a scalar, for a real number c, c times x1 dot 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 xn, this is being defined. Again, I will put a colon followed by an equal to, this is cx1, cx2 up to cxn. So, the vector addition of two elements in Rn giving back an element in Rn is quite straightforward. It's clear that this is an element in Rn, right. So, is this is also an element in Rn. So, Rn is certainly closed under these two operations. We are however left with the properties 1 to 8 that are to be checked to say that Rn is indeed a vector space. So, let me not go over all the properties, let me just focus on maybe one or two properties. Maybe let us check property 8. So, the multiplication is the multiplication linear. So, what do we have to check? We have to check that a plus b times x1 up to xn, is this equal? So, this is what we have to check, is this equal to a times x1 to xn plus b times x1 to xn, right. This is exactly what we would like to check. Okay. But what is a plus b times? So, let us start with the left hand side. What is a plus b times x1 to xn? This is component wise multiplication, right. Scalar multiplication by definition is a plus b times x1, a plus b times xn. But each of the components, if you observe, a, b and x1 all are real numbers, and we are just looking at the distributivity property of the real numbers, right. So, this is equal to ax1 plus bx1, ax1 xn plus bxn. But if you observe carefully, by the definition of vector addition, this is exactly ax1 up to axn plus bx1 up to bxn. And again, now we will use the definition of what the scalar multiplication is. If you look at the scalar multiplication of a with the vector x1, x2 up to xn, we get back ax1, ax2 up to axn. And similarly, if you look at the scalar multiplication of b with x1, x2 up to xn, we get back bx1, bx2 up to bxn. And that's precisely what we were trying to prove, right? This is exactly equal to what we have written here. Okay, so we have established the question mark. So claim, we have made a claim and we have given a proof. Now, this is just the property 8 that we have checked. There are 7 other properties, and the proof of each of the 7 properties, other 7 properties getting satisfied is very similar to how we would have done it in say R2 or R3. So, let me leave that as the first exercise for you, and I would strongly suggest that you really sit down and write each of these steps to check that property 1, 2, 3 up to 8 are indeed getting satisfied. Okay. A second example, example 2. Example 2 is the scalars, the field of scalars. So, R, the scalars F or R, let me call it R, is a vector space. Well, I think we just have to go up a bit and recall some of the properties which we were capturing. If you observe carefully, 1, 2, 3 up to 6 here satisfy most of the properties. I didn't even mention what our vector addition and scalar multiplication is. Let me go in a more organized manner. So, it's a vector space with vector addition as the usual addition of real numbers. And the scalar multiplication again, if you what is expected of a scalar multiplication here, a scalar and an element of the set V should give you back an element of the set V. So, here our set V is also R. So, you get a scalar and a real number. So, we can now just talk about normal multiplication, right? Scalar multiplication is the multiplication of real numbers. So, I was scrolling up, let me not do that again. The scrolling up part was to show that the various properties, the fact that R is closed under addition and multiplication is known to us, and the various properties, many of the properties have already been checked above when we described what scalars were or what properties of scalars we are interested in. So, this is a boring exercise, this is a boring example, but nevertheless, it is an extremely important example. A similar, not very interesting, but a very important example is what is called as the zero vector space. So, let V be the set which has just the 0 element. What are the operations? So, vector addition, we do not have much choice in talking about vector addition, there is only one element in the set V. So, we have to talk about what is the sum of 0 with itself, and we have not much of a choice again. There is only one element, it has to be 0 itself. And scalar multiplication. So, you take any scalar C and multiply it by the only element in V, it has to necessarily give you back the only element. Check that all the properties are satisfied. So, this is clearly the vector addition and scalar multiplication is being written in such a manner to ensure that V is closed under these operations. The properties 1 to 8 are trivially satisfied. This vector space is called as the zero vector space. Okay, so till now we have only seen examples which either is familiar or is not very interesting. So let's now consider an example. This is example 4. Let's consider an example which is a bit more exciting. So you might be familiar with the set of complex numbers. Let C, let me denote that set by C. So our vector space V is what is being denoted here by C. This is the set of all A plus IB, where A and B are real numbers. So if you have seen some operations in complex numbers, we have not defined in this course, but you might have seen that if you take say 2 plus 3i, and if you take say 4 plus 6i, and if you add it, you will get 2 plus 3i and 4 plus 6i, you will get 6 plus 9i, right? We will do it component wise in some sense. So C plus ID, this is being defined. So again I am putting a colon, this is equal to A plus C plus I times B plus D. So again, this might look like a bit of manipulation of symbols, but it is not exactly manipulation of symbols. So let me just show you what is happening here. The ones which I am circling in blue, they are just notations, right? The set of all A plus, we could have as well written it as A comma B, right? This is just a notation. The one I am circling in green is what is being defined. That is the addition that is being defined right now. A plus IB, which is a notation, and C plus ID, which is a notation for complex numbers, that is being added here by what is described in the right. In the right, let me use another color now. The yellow is being used, maybe yellow is a bad choice. Let me use blue, and let me circle the two additions that are written to the right hand side of the equation. Those are addition of scalars, those are addition of real numbers. Remember that A and B and C and D all are real numbers. So A plus C is a real number, B plus D is a real number. So we get back some real numbers. So there are many pluses which are featuring in this equation, and different pluses have different meanings. So it's very important to keep in mind that when we are doing some abuse of the notation, the context should make it clear, and that is something which we should familiarize with. Okay, enough said about the abuse of notations here. We have defined addition. So this is our vector addition, okay, that we would like to consider. Observe that if you are taking two complex numbers and adding it, you are getting back a complex number. Now for a scalar or a real number A in, let me note as R. So F is also F is used generally for the field of scalars, but in our case in this course most of our examples are cases when our field of scalars is real numbers. So I will use interchangeably between R and F. In fact, I will mostly use R. And C plus ID be an element of C, then define the scalar multiplication as AC plus I times AD. So scalar multiplication is also the most straightforward definition that we can think of. Again, notice that C is closed under this operation of scalar multiplication. And again, I leave it as an exercise for you to check that all the properties 1 to 8 are satisfied. So properties, let me leave it as an exercise. Properties 1 to 8 are satisfied by the vector addition and scalar multiplication. So if you have seen some operations, or if you have worked with complex numbers, you would have seen that we can also talk about multiplication of two complex numbers, and we'll get back another complex numbers. For example, a plus ib times c plus id is ac minus bd plus I times ad plus bc. But to talk about vector space, again let me reiterate, given two vectors v1 and v2, we do not talk about the product of v1 and v2. That operation is not being defined in a vector space. The only operation that we are defining is a scalar multiplied to a vector. So, even though it is possible to describe the multiplication of two complex numbers, for the purpose of studying the complex numbers, the set of complex numbers as a vector space, we will restrict our attention only to what is the scalar multiple of a complex number by a scalar. It is a good observation to keep in mind that this is just the special case of the complex multiplication of complex numbers that we might be already familiar with. But nevertheless, I have spent a couple of minutes exclusively to push forward the notion that given two vectors, given two elements v1 and v2 in capital V, we are not talking about the product of the vector the elements v1 and v2. I am using the word vectors. So, let me, before going into the next example, let me just give a definition. An element of a vector space is sometimes referred to as a vector. An element of a vector space is referred to as a vector of a vector space V, is referred to as a vector in V. So, when we say something is a vector in V, we just mean that it is an element in capital V. Okay, let us look at the next example, example 5. So, I will leave it as an exercise for you to check that all the properties 1 to 8 are satisfied, and I will strongly recommend that you really sit and write down and check each of these properties. Okay, what is the next example? Consider Pn of R. So, let V be equal to script P subscript n of R. What is this? This is the set of all polynomials of degree less than or equal to n. So, when I am asking you to check for all the properties, you are expected to come up with the candidate for what is the additive identity and what will be the candidate for the additive inverse of a given vector. Not just checking the remaining properties, you will also have to talk about what these additive identity and the inverses. So, let us now look at the example 5, which is polynomials of degree less than or equal to say n, where n is a positive integer. So, for example, if you look at P2 of R has elements of the type like say x square plus 1 or 2x plus 3. What else? Well, 4, the constant 4 is a polynomial, that is an element in P2 of R. All polynomials ax square plus bx plus c, where a, b, c are in the field of scalars, are real numbers, right. So, P2 of R will be the collection of all polynomials less than or equal to 2. Now, we are familiar with the notion of addition of polynomials. So, given two polynomials, we know how to add them. For example, if I say x square plus 4x plus 3 and if I am to add it to minus of 4x plus 2, we know that by basic algebra, we know that this is going to be x square plus 5, right. So, the addition is exactly generalizing this or rather putting it in a more formal framework, this exact vector addition which we are familiar with. So, a0 plus a1x plus, so let me just write the definition, vector addition, maybe I should leave that as an exercise as well. The next one we will, a0 plus a1x plus an x to the power n. This is the general, this is the expression for a element here, right. Some polynomial of degree less than or equal to n can be represented as a0 plus a1x plus up to anx to the power n, where a0, a1, a2 up to an are all real numbers. This is being added to say b0 another element b1x plus bn x to the power n. And what do we get? We get this is a0 plus b0 plus a1 plus b1 times x plus an plus bn times x to the power n. So, when we are writing it like this, the doubt that can crop up is whether we are considering the cases like in the example here. The polynomial to the right minus 4x plus 2, that does not have degree 2, right, that is a degree 1 polynomial, but that is okay because we have allowed b1 b0 where, so where a0 to where ai and bj all are in the field of scalars, right. So, in particular ais could be 0, all ais could be 0, a few ais could be 0, an could be 0 and so on, and still we can talk about the sum here. Okay, how about scalar multiplication? Scalar multiplication also, what if we take x square plus 4x plus 3 and multiply it by say 2, we will get 2x square plus 8x plus 6, right. So, scalar multiplication is also doing exactly the same thing that we expect. So, for a scalar c and p of x, a polynomial which is equal to say a0 plus a1x plus anx to the power n, define c times. So, remember that let me put a colon here because we are defining it. Similarly, we are defining it, the scalar multiplication here. This is being defined to be c times a0 plus up to c times an into x to the power n. Okay, so again I leave it as an exercise for you to check that all the properties listed in the definition of a vector space are satisfied. Okay, let us make it a bit more interesting. So, we were looking at polynomials of degree less than or equal to n. Let us not put any restrictions, let us consider all polynomials. So, let v equal to p of r be the set of all polynomials in the indeterminate x. Yeah, the previous one also was something like this. So, let me just put it in bracket with coefficients in real numbers. The previous one also was the set of all polynomials of degree less than or equal to n with coefficients in R. So, how do we define addition? We have already given you a glimpse of how we define the addition. I will not write it down explicitly. We can add any two polynomials. We can also talk about the multiplication of a scalar to a polynomial. We get back polynomials, right? And with the usual, let me just write it like this, with the usual addition and scalar multiplication, P of R is a vector space. So, let me give numbers here. This was example 6. Okay, example 7. So, this is an example which is not similar to what we have seen till now. So, let V be equal to C of R, where C of R is the collection of all functions from R to itself such that f is continuous. So, you have, if you have seen the notion of continuous functions, let us look at the set of all continuous functions from R to itself. Okay. So, we define the vector addition here. Let us define for f comma g in C of R, f plus g. So, we need to describe f plus g should be some function from R to R, right. So, we will define f plus g of x to be f of x plus g of x. Now, notice that this makes f plus g into a function from R to R, and some more background in real analysis will tell us that whatever we have defined turns out to be continuous as well. So, the closedness is something which I will not verify now and leave it for you to verify later after doing a Coase and real analysis. And the scalar multiplication. So, this is the vector addition we have just defined, right. Scalar multiplication, again C times f. This is as of now just a notation, and let me say how this is a function on R. This is defined as C times the scalar C times, now f of x is a function, f is a function from R to R, f of x is hence a real number. So, C times f of x is another real number. So, define Cf to be this particular function. Again, I will leave it as it is not an exercise. Let me leave it right now to check that multiplication of a scalar by a continuous function gives you back a continuous function. That is something which I will rest right now, and let you verify this later when you do a Coase on real analysis. So, the fact that C of R is closed under vector addition and scalar multiplication will be taken for granted right now. So, let me just write that down. C of R is closed under vector addition and scalar multiplication. Okay. And an exercise is to check that properties 1 to 8 are satisfied. So, interesting question to ask might be, what will be the 0 vector of C of R? I will let you think about it. Let me give you more examples. So, example 9. Or not, example 8. Let V be equal to what is usually denoted as f of R. So, you might be wondering why I am giving strange notations. These are all classical notations, and f of R is used to denote the set of all functions from R to R. Set of all functions from R to R, and define vector addition and scalar multiplication as in example 7, pointwise. It is good to again sit down and check already most of the things have been checked. If you have done the exercise, previous exercise, if you do the previous exercise, this will also follow. F of r is a vector space, is an exercise to be checked. The fact that vector addition and scalar multiplication will give you back an element in f of r is quite straightforward. It is the properties which you have to check, but I think the previous exercise would have already done, you would have done most of the work. So, with that, f of r is also a vector space. So, we started off with just very basic examples like R2, R3, Rn, and now we are looking at spaces which has functions in it, and we are saying that these are vector spaces. They are similar in some sense, at least some of the properties of the addition and scalar multiplication are the same as the properties of the addition and scalar multiplication in Rn. I'll maybe give a couple of examples more. They are important examples, and hence, so let R infinity be the set of all infinite sequences. So, sequences. So, an element in R infinity will be something like, say, 1, 2, 5, 6, 1, 4, dot, 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 an infinite sequence. So, formally R infinity is just the set x1, x2, dot, 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 such that xi belongs to R. And how do we define vector addition? Again, pointwise, just like how we define it in Rn, define vector addition and scalar multiplication in R infinity as well, and check that it is a vector space. So, I will just write it as R infinity is a vector space with vector addition and scalar multiplication defined as in similar to the ones in Rn, coordinate wise. Okay. So, let me give you just one more example finally before going ahead. So, example 10. Example 10 is again the classical notation is m cross n of r. This is an example which you will be quite familiar with, where m cross n of r is the set of all m cross n matrices. So, this is the set of all a11, a22 up to an1 dot 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 am. So, m cross n of r formally is the set of all elements of this type a11, am1 up to amn, where aij are real numbers. So, what would be the vector addition and scalar multiplication? Again, vector addition and scalar multiplication is coordinate wise. Is defined coordinate wise. I will not write it down, it is just going to make it cumbersome, and it is something which you can very easily do. So, let me leave it as an exercise for you to write down formally what the vector addition and the scalar multiplication is, and again I leave it as an exercise for you to check that all m cross n matrices over R is a vector space with these operations. So yes, so we have now defined what a vector space is, and we have seen many examples of vector spaces. There are actually plenty of examples, infinitely many examples of vector spaces, but let us not go into it more. We will be keeping on visiting more examples during the course. Many new vector spaces will be defined from existing vector spaces and so on. Okay, so now that we have spent so much time to talk about examples, let us also discuss a few cases which will be non-examples, non-examples, non, non-examples. So let me just write it down, non-examples. So one example would be, consider all polynomials of degree equal to n. So let V be equal to the set of all polynomials of degree equal to n. Well, I will give you your favorite pick of which property is getting violated. So, in fact, even before we enter into properties, notice that V is not closed under addition, for example. If you take a polynomial, say x to the power n plus 2, and if you add it to minus of x to the power n plus 5, what we end up is 7, right? If n is say 2, if you are looking at P2 polynomials of degree equal to 2, 7 is certainly not a polynomial of degree 2. So, this set is not even closed under vector addition. So, this is certainly not a vector space. So, the first requirement before we start looking at the properties is that it has to be closed. If you take two elements in the vector space in the set, if you add it, you should get back an element in the set itself. That is not getting satisfied here. What could be another example? Yes, so another example is, consider R plus. R plus is the set of all positive real numbers. So, if you take, so here the addition and the scalar multiplication is defined like we define it in the vector space R. So, if you take two positive real numbers, if you add it, you get back a positive real number. So, R plus is closed under addition, and if you do the scalar multiplication, now the problem comes, is it closed under scalar multiplication? Answer is no, it is not closed under scalar multiplication. If you take say 2, and if you look at the scalar multiple of minus 1 to 2, then minus 1 to 2, the minus 1 and 2, the scalar multiple should be minus 2, which is not an R plus. So, this is not closed under scalar multiplication. So, with vector addition and scalar multiplication as in R, then this is not closed under scalar multiplication, it will not be a vector space. Okay. So, we have discussed quite a few examples now, we have seen maybe a couple of non-examples. Let us see what the impact of the properties are on various vector addition operation, on the vector addition operation and the scalar multiplication operation. So, maybe let me give a proposition. This is the first proposition of this course. So, let V be a vector space and suppose U, V, W are vectors. Suppose they are elements in the vector space V, then U plus W is equal to V plus W, then if does not sound good, if U plus W is equal to V plus W, then U is equal to V. what does this proposition tell us? The proposition tells us that if you have a vector w, which is the vector basically cancels, that is what it says, right? You can cancel off vector w, which is featuring in the left hand side and the right hand side, and we get u is equal to v. Let us give a quick proof of this. This is the first proposition of this course, so let us spend some time to talk about how a proof can be given rigorously. Okay, so what is it that we know? We know that V is a vector space, and given any vector space, we have that every vector has its additive inverse, right? So let minus W denote the additive inverse of small w. The element W has an additive inverse, let us denote it by minus W. Then u plus w is equal to v plus w implies, by adding the vector minus w both sides, nothing changes, u plus w plus minus w is equal to v plus w plus minus w, right? But our vector addition is associative. This implies this is equal to u plus the above u plus w plus minus w is the same as u plus w plus minus w. The which two vectors are added first does not matter. Similarly here, w plus minus w, but minus w is the additive inverse of w. So, if you add w and minus w, you get u plus the 0 vector, which is the same as the v plus the 0 vector. Notice that when we write the 0 here, it should not be confused with the scalar 0, the real number 0. This is an element in the vector space V, and it is clear from the context what it is. U is a vector in capital V, and therefore you cannot make sense of u plus the real number 0. So, here when we write u plus 0, it is clear from the context that 0 is the 0 vector of capital V. But what is u plus the 0 vector? It is just u, and this is just the V, and hence we have proved the result. So, let us just for the sake of completion, even though I said it very orally, what is this implication coming from? Since addition, vector addition is associative, important to note all the reasons. Why is this happening? Since minus w is the additive inverse of w. So, you should go back and check which property of the definition of the vector space we have used, and this because 0 is the, since let me write as since 0 is the additive identity. Okay. This symbol will generally denote that we have completed the proof. I will give a few exercises here before concluding this session. Prove the following. One, 0 times any vector v is equal to 0. This is a good exercise for you with the abuse of notation that we are getting familiar with. So, if you observe carefully, the left hand side is the scalar 0 multiplied to V, the scalar multiplication of the real number 0 to V. So, this is the, so let me just note that this is the real number 0 and this is the 0 vector in V. To prove the following, in any given vector space V, so this is true for all V in capital V. Okay, what next? Prove that if you look at minus 1 times V, this will give you minus V. So, for all V in capital V, what is minus V? Where minus V is the additive inverse of V. Okay, so we have just written the additive inverse. So, that's not something acceptable yet, because what forces the inverse to be unique? Could have been an additive inverse, right? An additive inverse would have been more appropriate here. So, to do that, let us do one thing before we go into other examples or other exercises. Let us prove the following: the additive identity and additive inverse of any vector is unique. So, first we will show that the additive identity is unique, and then we will show the next part. Okay. So, suppose there are two different, so suppose 0 and 0 prime are two identities, additive identities. What is the property of an additive identity? If you add any vector to that, it should give back the vector itself. So, 0 in particular is equal to 0 plus 0 prime, right? But what is 0? 0, this is because going by the assumption that both 0 and 0 prime are additive identities. So, in particular 0 is also an additive identity. So, if you treat our 0 prime as our vector V, and if you add it to 0, because 0 is an additive identity, you should get back V, right. So, this is equal to 0 prime, and why is this equality coming up? So, this equality is because of this equality is because since 0 is the additive identity. So, let me not give a proof of the inverse being unique. I will leave it as an exercise for you to check that inverse is unique. Idea is more or less similar. Check that the inverse, check that the inverse is not yet right. We have, that's precisely what we are trying to do. Inverse of any element V, any vector V in capital V is unique. All right, let's stop here.